So you've read this, I think. The photograph shows the active parts of the solar panel at full size. By taking measurements from this full-size photograph, shows that the total area of active parts of the solar panel is 10 to the minus 3. Include the uncertainty in your answer. So this is a photocopy that is made bigger. So I can't actually measure it on here, but if you do, then you find that this side here is 7 millimeters. So that bit there. And this side here is 6.3 centimeters. So that is what it should be if you've got the actual size photocopy. So we can find the area. Well, we've got 3 of these things. 3 times 6.3 times 10 to the minus 2 times 7 times 10 to the minus 3 will give you an area, total area of 6.3 times 10 to the minus 2 times 7 times 10 to the minus 3 of 1.32 times 10 to the minus 3 meters squared. So that's okay for our area, but we've got to estimate the uncertainty. So we are certain about that number. That's got no uncertainty because there's definitely 3 of them. Okay, so that's got 0 uncertainty. So we need the uncertainty in this and the uncertainty in this. So the percentage uncertainty, well, let's call it the width and the height, maybe in H, is going to be the nearest millimetre, so 0.1 centimetres over 6.3 centimetres times 100. The percentage uncertainty in the width is 1 millimetre out of 7 millimetres times 100. So 0.1 out of 6.3 times 100, that is 1.59%. 1 out of 7 is 14%. So the total percentage uncertainty is 15.6%. So 15% of this, 15.6 times 1.32 times 10 to the minus 3 divided by 100, 15% of that number, 15.6% of 1.32 times 10 to the minus 3 is 2.0 times 10 to the minus 4. So actually this is plus or minus 0.2 times 10 to the minus 3 meters squared. So they do actually want you to calculate the absolute uncertainty of the value as well. Okay. The following results were recorded when the team tested the hat in a laboratory. Intensity of incident light, output current, output potential difference. Determine whether the team member's statement about the efficiency is correct. So we can get the output power is just P is equal to IB, which is 102 times 10 to the minus 3 times 1.52, 102 10 to the minus 3 times 1.52. The output power is 0.155 watts. Input power we've got this many watts per metre squared, and we've got this much area. P is equal to the intensity times the area. So 1240 times 1.32 times 10 to the minus 3. One point six three, 1.63, no, 1.64 maybe, 1.64 watts. So efficiency is the useful power out divided by total power in, 0.155 divided by 1.64 times 100, 155 divided by 1.64, 9.45%. So their original statement is about 10%, that's what we've got. This is about 10%. So statement is correct. Okay. Criticise the comment that our hat could make significant energy conservation and protecting the environment. Well, look at this power. Less than 1 watt. This is a tiny amount of energy. This is very insignificant. 0.155 watts is tiny. So will make no useful contribution to the environment. You should have an idea in your head about the power of things around you, like a light bulb. A light bulb is about, or an old-fashioned light bulb is about 60 watts. This is nowhere near even 1 light bulb, so it's fairly useless, really. Okay. I mean, the other thing that you can say is that this is a solar-powered hat, which is a fairly useless thing. So it's not really going to contribute to protecting the environment. To manufacture this thing will use a lot of energy as well. The hat is something we don't need. The energy needed to make the hat is much larger than what you save from batteries.